Now, in this question, what we're going to look at is how much carbon dioxide is created by burning a certain amount of gasoline in your car. Now, for this question, we're going to assume that this gasoline that's burned does not contain any ethanol, which is a common additive to your gasoline to basically keep things running as they should inside your engine. I'm going to assume that your gasoline is 100% octane. Now, octane has the chemical formula C8H18. Now, because this organic molecule, octane, has so many carbon and hydrogen bonds, it's very efficient. When you break those bonds, you get a lot of energy out of the breaking of those bonds, and the internal combustion engine inside your car is specially designed to collect as much of this energy as it possibly can. Now, with the balanced chemical equation, as it says here, we're going to assume that it's complete combustion. In complete combustion, a hydrocarbon reacts very vigorously with oxygen gas that's generally present in the air. In your car, there's an oxygen injection system that makes sure that enough oxygen is there to burn that octane. To make sure there's enough oxygen there to burn that octane efficiently. The most efficient way to burn a gasoline is through complete combustion. When you completely combust a gas or a fuel like octane here, you'll end up with only two products to the reaction. You'll end up with carbon dioxide and you'll end up with water molecules. When you don't burn it completely because there's not enough oxygen there, then you also end up with carbon monoxide, which is obviously very poisonous, and soot, which is just essentially ashes. And that can kind of gum up your engine when it gets stuck in your fuel injection and the other systems that are inside your internal combustion system. Now, the first thing I want to do before we do this question is balance this equation. What we're looking at today is stoichiometry. And stoichiometry only works when you have a balanced chemical equation. What stoichiometry basically means is what's the ratio or how many molecules of each of the reactants need to combine to create how many molecules of each of the products. Now, because of Avogadro's number, we can use ratios of molecules just like we use ratios of moles. So using stoichiometry, it allows us to do things like calculate how many grams of carbon dioxide are created based on how many liters of gasoline were burnt. Those ratios allow us to convert from one of these products or reactants to any other product or reactant. But it only works if the equation is actually balanced. So I'm going to balance the equation really quick here. Let's do it through magic just to save some time. And abracadabra, there I am. I guess even magic has some mistakes in there. So I managed to get that balance there with 2 in front of the octane, a 25 in front of the oxygen, 16 carbon dioxides, and 18 water molecules. Now, when it comes to stoichiometry, the best way to read this is using the numbers that are involved. So if I were to look at how many octane molecules react with how many oxygen molecules, it takes 25 oxygen molecules to completely combust 2 octane molecules. And if they do that, that produces exactly 16 carbon dioxide molecules and 18 water molecules. Now, obviously, 2 octane molecules is not a lot of gasoline. So what that does is that makes these ratios or these numbers in front of the reactants, coefficients in front of the reactants, also relatable in moles. So instead of saying 2 molecules of this react with 25 molecules of this, we could just as easily say 2 moles of this react with 25 moles of oxygen, and that creates 16 moles of carbon dioxide and 18 moles of water. And 2, 25, 16, 18 moles of a substance is much more relatable in the macro scale that we live in. You know, that could be a kilogram or 2 of some of these substances, a normal amount. Now, like with all questions, we always want to start by writing down what we know. That's always the first step. Write down all the values you know. And in the cases where you have to deal with stoichiometry, you're probably going to want to calculate the molar masses of at least the things that the question's asking you about. In this question, it's telling me how much octane I have, and it's asking me how many grams of carbon dioxide I have. So I'm going to make sure I calculate the molar masses of those two things. Let's put those right here. Abracadabra, there are the molar masses of those two chemicals that we're particularly interested in this question. I also need to write down that I have 3.6 liters of gasoline because the question has told me as much. And the other thing the question's told me is the density of gasoline, which is 0.74. Well, let me fix that up. Look at that. I can even undo the mistakes I made previously. Sorry, it's 748.9 grams per liter, not 0.7489. Just converted that density incorrectly and just realized it totally before now. I hate to waste good video, so I may as well use it. So let me write down that quantity as well of 748.9 grams of octane per liter of octane. Now, this unit elimination question is going to involve switching a lot of units around. We're actually going to have 4 values that we have to use, in addition to some other values as well. So this is going to be quite the equation when we're done. But like the previous question, the point is to start with the target that you're trying to get to. I'm trying to get to grams of carbon dioxide. That's my target. So I'm going to start by writing that down with that equal sign there. I want to eventually end up with that being the remaining unit. The problem is I'm starting with liters of octane. So I'm basically going to slowly convert liters of octane 1 unit at a time until I end up with grams of carbon dioxide at the end. So let's give it a go here. Let's start with our 3.6 liters of octane. Now I'm just going to use the short form oct for octane just to save a little bit of space there. And, because I have so many units here, I'm actually going to check these off as I go so I don't accidentally reuse a unit that I already have. Now, I want to eliminate liters of octane. I only have 1 unit here, or 1 value that has liters of octane in it. It's right here. It's the density of octane. And I want to leave liters of octane in the bottom. Okay, so the 748.9 grams of octane is going to go in the top, and the 1 liter of octane is going to end up in the bottom. Now we can cancel those 2 units out and move on to the unit that we have left. The unit we have left is grams of octane. All right, let's check this off because I used it. Now, which of the different units do I have that have grams of octane in them? Well, it's going to be the molar mass of octane. That's going to let us change from grams of octane to moles of octane. Now this time I'm going to want to leave grams of octane in the bottom. So I'm going to put the 114.2295 grams of octane in the bottom. And I'm going to put the 1 mole of octane in the top. That's going to allow me to cancel out grams of octane with grams of octane. And my new unit that I have is moles of octane. This is a good time to go back and check, do you have the unit you're looking for? Because you don't want to go too many steps in. Sometimes you'll get to the right answer and you'll multiply it again and change it from the right answer to the wrong answer. So always check once in a while to make sure the unit you have here and the unit I have here don't match up, indicating that your question is complete. And in this case, obviously, we do not have that situation. All right, let's check that off because we've used it. Now, the unit I have left now is moles of octane, and the only unit I have left to use, or the only quantity I have left to use over here, has moles of carbon dioxide. So this isn't really going to help me right now. This is where stoichiometry is going to come in. I want to eliminate moles of octane, and this is my opportunity to change it from moles of octane to moles of carbon dioxide, the thing I actually want to find. This is where the stoichiometric ratios are going to come in. I know that 2 moles of octane react to create 16 moles of carbon dioxide. And why is that? Well, it's because of the stoichiometric ratios here. Right? 2 moles of octane, when reacted, are going to create 16 moles of carbon dioxide all the time, every time. So I can use this ratio to cancel out moles of octane with these moles of octane here and leave myself with moles of carbon dioxide, which means I'm getting a lot closer to the final unit that I want. That leaves us with our very last value here, which is molar mass of carbon dioxide. And I want to put the 1 mole at the bottom. And then the 44.0096 grams of carbon dioxide go in the top. My last time I have to eliminate units is right here. So those 2 units eliminate. And now I have the unit that I wanted when I started, which was grams of carbon dioxide. So I should be able to write out all these values for the math it section at the bottom. All right, so I've got the 3.6 liters to start. Again, at this point, you don't have to worry about the units. You can just worry about the numbers. I'm going to multiply that by 748.9. Okay, that's that one there. Then I'm going to divide that by 114.2295. I'm going to multiply that by 16. But then I'm going to divide that by 2 because I've got this 2 in the bottom of this fraction. And then finally, I'm going to multiply that by 44.0096. Remember, all of the 1s can be excluded because multiplying or dividing by 1 doesn't change the number. And again, you don't have to worry about the units anymore because you've already canceled them all out. You know the final answer is the unit that you want, so you just basically have to figure out the math. I'll put that in the calculator and put the answer right here using magic. And abracadabra for the final time. Oh my gosh, I didn't even put it in a box or circle it or even underline it or anything. I'm going to make sure that stands out. So I got 8,300 grams for this. I had to round it to 2 significant figures. It was actually like 8,310 grams, but you know, sig figs got in the way. Just remember that that 16 and the 2 do not count as sig figs because they are exact values. So you don't have to worry about those for significant figures, only the measured values that the question gives you, as well as the sig figs as limited by your molar mass and the density I gave you and whatever else you got. All right, that's it for this one. We're going to do one more stoichiometry question in the next video, so stay tuned for one last ride through Thrill Town.